one is a math lab, but we are going to do it together. So as a warm-up, can you write domain and range for each of these three graphs? I'll put the answers up in a second. Pausing two. What did you do? So the last one has asymptotes. It would have an asymptote here and an asymptote there. Horizontal asymptote, the graph doesn't go through it, so our range y can't equal 0. Now, in math, all the way through school, we go right back to kindergarten and grade 1. What are some of the very first math things you did? You counted, and then you went on to adding and subtracting, probably before multiplying, but then you went on to multiplying. And if you look back right from kindergarten, grade 1 up until now, you haven't stopped adding, subtracting, multiplying, or dividing ever. You keep doing it. But math adds things to it, right? I think, I don't know, if in grade 3 or 4, they're like, you have to learn your times table, but not past 5s. That would be terrible if someone learned 6 times 6 early and ruined them for life or something. But then the next grade, you learn a little bit more. And then a little bit later, it's sort of like, oh, we're going to add, but now we're going to add letters. Well, there were variables, right? But for when you were first like, we're adding letters now. X plus X is 2X. That was a new kind of adding and a new kind of multiplying. And then we got into factoring, which is like a new kind of multiplying and dividing. And so we work through this and keep adding things and doing things and sort of like, well, if we've been practicing adding and subtracting, and we started with numbers, and then we included variables, and then we included trig equations and adding equations and stuff. What haven't we added and subtracted yet? And that's what we're going to do today is graphs. If you have a graph plus another graph, the answer is you get another graph. And that's what we're going to be doing. So here's our first example. It has two graphs, and we're going to want to add them together. They say in this question that this is enrollment in university and in college. So graph function A is college enrollment, and function B is university enrollment, and they have different years here. So we could read this graph and say, well, in 2004, there was just over 6 million people enrolled in colleges across Canada. Does it say where? Could be the whole, no, it is Canada across, yep. And just over 10 million in Canada. So in 2004, if we wanted to find the total number of people enrolled in secondary education, we would have to add those numbers together. So this is the idea of adding graphs. If this is one graph and this is the other graph, you go to your y values and say, well, if there was just over 6 million and just over 10 million, I'm going to say there's just over 16 million in 2004. If we go to 2005, just over 6, like 10 and a half, a little bit more. 2006, just over 6, oh, just about 11. I'm going to say that that would be really close to 17. And now we're 6.2, and this one looks like it's gone up a little bit more. And then finally, over 11 and over 6 would be over 17. So we add the y values. If you have a graph and you want to add another graph, all you have to do is just add the y values, and that's what graph plus graph equals graph looks like. We're going to find that this theme of just looking at the y values happens with subtracting, dividing, and multiplying. You're just going to look at your y values, and if you have two graphs that you want to add or subtract, that's going to be what it looks like. So let's look at example 2. Here they've got a couple of graphs. They have a stopping distance graph, a reaction distance graph. This is you driving a car, okay? If you're driving a car and something comes out in front of your car, you should want to stop so you don't run into it, okay? Now, cars are designed so that when you hit the brakes, you don't stop immediately. They could probably make cars with like spikes that go right into the ground. So as soon as you touch the brakes, you stop instantaneously. Do you know what that would do to your body? It would be like your whole body would just like, every time you hit the brakes, you'd have like seatbelt bruises. I mean, but you could design that. But normally what happens is if you stop, if you slam, have any of you ever like slammed on your brakes? So that's a little scary, but it does jerk, but you slide a little bit, right? That's what this stopping distance is. The faster you're going, the more your vehicle is going to slide forward. That makes sense, okay? There's also this reaction time distance, okay? When something comes in front of you, you have like, and then that reaction says, I should slam on my brakes, which your brain has to go down to your foot has to move, and it has to go quickly to slam on your brakes. That takes time. Usually that time is pretty quick, right? But still, if you're traveling fast, you're going to travel a little distance before that happens. So, how far you stop? First, you have to react. And in that reaction, for example, here at 100 kilometers an hour, it says you go 20 meters before you've even hit your brakes in your reaction. Then you slam on your brakes, and then your total stopping distance is just 110. Does it make sense that you would have slid 90? Oh, these are not quite lining up. Sorry, I'm not looking at the circle. 20 and 90, you would have slid 70 to go there. So if we look at the equation they gave us, they said the stopping distance, which is the red graph, is equal to the reaction time distance, which is the blue graph, and we want to find out in green, what is our actual braking distance? If I wrote this in letters, stopping equals reaction plus braking. Does it make sense that you could rearrange this and get the braking by itself by doing the stopping minus the reaction? And since we have the stopping graph and we have the reaction graph, to find the green graph, we have to subtract. And what do we do? It's pretty straightforward here. Just like last time where we just added the y values, if you have two graphs and you want to subtract them, you just subtract the y values. So we'll do a little bit of estimating. Here it looks like we're at about 58. Here it looks like we're at 16. 58 minus 16 would be at about 42. I like this point right here. You're in a parked car. Somebody runs out in front of your parked car. You go, you react. I should slam on my brakes. How far do you travel during that reaction? You're parked. You don't travel anywhere. But then you slam on your brakes. How far do you travel after slamming on your brakes if you're not moving it? You don't move anywhere. And your stopping distance would be exactly where you were to begin with. So if you're not going very fast, if you're going 20 kilometers per hour, you can stop within 10 meters. Which just still seems pretty far. It means anything that was from here to even at 20 kilometers an hour, which isn't very fast, but like anything at the wall there, you would still hit them. Which is why it's really scary. Have you ever seen deer run across the road? Has anyone ever seen a car hit a deer? Yes. Because they don't take that into consideration. The deer are not very thoughtful that way. They just jump out right in front of you. You can slam on your brakes all you want, but there's no chance of you stopping. So if we do all of these ones here, so this would be 10 minus, that would be about 5. This one is 20 minus 8 would be around 12. Here we got 35 minus 12, around 23. And that looks like that would be our braking distance in there. I saw a deer get hit probably a month and a half ago. It ran across our lane of traffic and nobody hit it. And everybody was like, ah. And then went into the other lane, boom. It's like so sad. Oh. Okay. I'm going through trauma here of, I'll tell you a little traumatic story. Next, they didn't even make a story for this one. They just said, here's a parabola and a square root graph. Let's multiply them together and see what happens. So you got f of x, g of x, and we want to multiply them together. Well, with adding, we just added the y values. With subtracting, we just subtracted the y values. Well, what do you think we're going to do with multiplying? We're going to multiply the y values. So if we had the two graphs and we're asked to multiply them, we're just going to take y values and multiply them. Now, there's going to be some strategies involved here. Some multiplications are easier than others, right? Because if you get to ones that you're estimating, like 2.3 times 3.7, and then you're like, oh, mental math sort of goes bad there. So what are some multiplying ones that are really easy? 0. If you find any zeros, so let's, and that 0 can be on either one. Like here they're both 0. 0 times 0 would be 0. Can you see that at 2, the blue graph is 0, the red graph looks like 1.5. Does it matter what the red graph is if the blue graph is 0? No, that'll be 0. So that's a good strategy. Any place where one of the graphs is 0. What also is easy to multiply by? 1. So I'm going to mark where the blue graph is 1. And I'm going to mark where the red graph is 1. Now something interesting happens happens with the first place, the blue graph is 1. Because if we just multiply the y values at the same x value, the blue graph is 1. The red graph doesn't exist. So I'm going to give you a question and see how well you can answer it. What is 1 times...
Sorry for the interruption. Would student council representatives from grades 9 and 10 please come to the office? That's student council from grade 9 and 10. Please come to the office.
Okay, we'll start that again. If I just said, what's 1 times... and I didn't say anything else, you would just be there waiting for me to say, there's nothing you can say, right? So for this first point, there's nothing we can do for the green graph. You need the y values to exist for both of them. This is true for adding, subtracting, and multiplying, and dividing as well. You need the values to exist in order to multiply. But when we get to the second place where the blue graph is 1, the red graph looks like it's at about 1.6. What's 1 times 1.6? Does it make sense that this green dot would be, well, attempting to put this green dot right on the red graph? Does that make sense? When you multiply by 1, it's not going to change. Here the red graph is 1, and the blue graph is minus 1. What's 1 times minus 1? Minus 1. Does it make sense that this point would be on the blue graph, exactly where it is? So if either graph is 1, when you multiply, your other point is going to be on the other graph because it's not going to change. Now if you can find any other nice points, you can multiply them on there. But you might have to do some estimating, like this looks like 3. I could take a point here. This is 3. This looks like 1.8. What's 3 times 1.8? 5.4? Yeah, so we could do other points here. Does it make sense when you do a positive times a negative that your answer in between here will always be negative? And that a positive times a positive, this part of the graph will be positive? So if one graph is positive, the other graph is negative, because a positive times a negative, your final graph should be negative.
How are you sure the green graph is not going to go outside of the green line?
Well, and then here the idea is if I multiply, the red is bigger than 1 and the blue is bigger than 1. When you multiply, your numbers would get bigger than that. So that's why your green graph would be higher than both your blue and your red graphs. It's a little bit harder to visualize the multiplying because it's a little bit more complicated there. But definitely going to use zeros and ones. Do any other values that you can multiply, because you're just multiplying the y values. And it's just more mental math to sort of figure out where it's going to be after that. So maybe we write in our strategies here. Right? There, I can write this like this. If you had a negative times a negative, you'd get a positive and etc. there. So depending on where your graphs are, you can use that as kind of hints of where your graph should be. Okay? How accurate do they want your graphs? They want to make sure that they see the zeros and the ones because they're easy. Any other easy points that you could do, right? You can always add more points, but just a general idea of what the graph looks like. And then the most complicated one is divide. So, the basic strategy is exactly the same. You just divide the y values. I'm going to color code this. They want g of x is blue, and f of x is the red graph. So we want to take the red graph and divide it by the blue graph. What are some important things about dividing that we've learned over the years? Can't divide by 0. So what this is going to result in asymptote. Very rarely, I don't think I've ever seen it, but it could be a possibility that it's a whole. Asymptotes or wholes, because remember, if you're dividing and you have a non-permissible value, sometimes it's an asymptote, sometimes it's a whole. Almost always in these questions, there'll be asymptotes. But in this case, since we're dividing by blue, we're going to have an asymptote or a whole wherever g of x is equal to 0. In this example, they will be asymptotes. The only way on a graph that you would get a whole, does it make sense that the graphs would have to cross there? They both have to have the same x-intercept? Because then that factor would cancel out with the factor on the bottom. In our examples, in almost every example, they're going to have ones like this, where you get asymptotes. I think there might be one example in the whole market with a whole. So you can't divide by 0, absolutely. Zeros are very important. As a strategy, if the red graph is equal to 0, and that's the graph on the top, does it make sense that f of x over g of x, if you have 0 on the top of your fraction, it's going to equal 0? So strategy-wise, I'm going to draw asymptotes where I have the blue graph is 0, because those are non-permissible values. Where the red graph is 0, I know that the whole thing would equal 0. So I can add a green point there. What else is easy to divide? We can still do the same strategies of positives and negatives, right? Because positive divided by positive will be a positive number. Positive divided by a negative will be a negative number. So we'll use that strategy kind of like multiplication. But there's another easy thing to divide that appears on this graph. There's always nice points, but there's one point in particular that even if the points aren't nice, I guarantee you can divide. Sorry, any ideas? If you're dividing by 1, yes. Dividing by 1 is super important. So, if we're dividing by 1, so g of x is 1, here and here. What's going to happen when you divide by 1? It stays the same, right? So that is super easy to do. That'll be here. Straight up would be there. Those 2 points would be the same. Excellent. So, we'll write that down. So that would be the g of x equals 1, not the f of x. We're only worried about where the blue graph is equal to 1. And there's one more strategy I'm gonna put up here that also is nice and easy for dividing. Give me a random number. 8. Okay. What's 8 divided by 8? 1. Good job. Good mental math. All right. 8. As far as difficulty goes, I would say 8's a pretty easy number. Give me a hard number. 272. What is 272 divided by 272? You guys are amazing. Okay. What happens if I go even harder? Like, give me a number with 3 decimal places. 4.038 divided by 4.038. 1. You guys are impressive. This is after holidays. You come back and your math skills are already at this high level. Does it make sense that if the red graph and the blue graph are the same, and they intersect, I'm going to put it in purple, they intersect right here and right here. If they're the same and you divide them, what are you going to get every single time? You're going to get 1. So that's another strategy. If f of x and g of x are the same, you're going to get 1. So, based on what we have here, it looks like this is going to go towards our asymptote this way. And we could estimate values on the other side here. This looks like we're going to have 4 divided by a negative, I don't know, maybe 4 divided by negative 4. I'm going to estimate that at negative 1. Same thing over here. This looks like it's going to be 4. If this kept going, maybe it would be at negative 4. This is going to go towards the asymptote in this direction. Okay, what else could I do here? And sometimes in these graphs, okay, you're going to have to use, like we're dividing, we're going to have to use chapter 2 in our rational functions unit. Does it make sense that this side over here is a straight line? And this is a parabola. And if you had a line divided by a parabola, the degree is bigger on the bottom. What did you get in graphs where the degree was bigger on the bottom? You got an asymptote at y equals 0. So that's giving us a hint. This goes like that. Wow. Adding and subtracting graphs almost seems so easy they could probably teach you that in grade 3. And you'd be like, I got it. The dividing graph is definitely a grade 12 concept because you have to use our chapter 2 about looking at the equations and guessing what you're going to get, and a whole bunch of strategies to figure them out. Actually, a really good strategy, even in the last one, if you look at this, this is a parabola times a square root graph. Sometimes you can do that. Like, if I took a parabola and I times it by a square root graph, is that a graph that we've worked with a lot? No. So I don't know the shape of it. But sometimes you're going to get equations that are parabolas times straight lines. And if you took an x squared graph and multiplied it by an x graph, you're going to get an x cubed graph. And since we've graphed x cubed graphs, you'd have an idea what it could look like, even before you've drawn it. So sometimes knowing and recognizing the original shapes will be helpful for figuring things out as well. Okay, so that is all of 4.1.